Good evening, everyone. Today I'm excited to talk to you about Homebrew at scale. So basically, I'll focus on our automated CI builds and also ARM64 Linux support. Maybe let me start by briefly introducing myself. So my name is Ruoyu, and I'm currently a Master of Computing student here at NUS SOC, and I specialize in Infocom security. And I'm an active open source contributor since 2022, and I've contributed to several projects over the years, and that includes Homebrew. And I've been a Homebrew maintainer since 2023, that's 2.5 years ago. And earlier this year, I also assumed a seat on Homebrew's technical steering committee, where I help to maintain Homebrew and to guide Homebrew's technical direction. So if you happen to have Homebrew installed, my name is at the end of Homebrew's man page. You can find my name at the end of Manbrew. So here are the topics to be covered in this talk. So first, I'll give a very brief introduction to what Homebrew is, in case you don't know it, and share a little bit about myself and my journey as a maintainer. And then we'll dive into the main content, which is Homebrew's bottles and CI infrastructure, where I'll explain how we build and distribute binary packages at scale. And also, we'll discuss our recent work on porting Homebrew to ARM64 Linux, which is also a great example of how scalability enabled us to support new platforms effectively. So what exactly is Homebrew? So maybe can I get a show of hands? How many of you know what Homebrew is? OK, how many of you use Homebrew? Oh, quite a lot of you. OK, so for those who are not familiar, Homebrew is the missing package manager for macOS, and it's actually also available on Linux as well. And we have tens of millions of users worldwide who use Homebrew to install software on their systems. And Homebrew can install software from source code, but more commonly it installs from binary packages that we call bottles. And we maintain over 7,000 official formulae, and formulae are just package definitions in our core repository called Homebrew core. And you can see that we use a lot of terminology related to beer, like the name Homebrew itself, like formulae and bottles. And if you ask me why, I guess I can answer that with the very first commit from the Homebrew repository, and you'll see even more of them later. So how did I become a maintainer? So my journey with Homebrew began when I first got my Mac in 2021. And as a new Mac user, Homebrew came in very handy for installing the software I needed so that I don't need to check out the official websites, download all the package installers, install them manually, and worry about the updates. And my first contribution to the project was a simple pull request that updated a formula called GraphViz to a new version. And because the version was outdated and I needed a very specific bug fix from the new version. And Homebrew made it very easy for me to make the contribution, so from there I started to contribute more regularly. And I also tried to fix bugs in formulae and also solving some complex build problems, and I also tried to add some new formulae. And after being consistently involved over time, and I was invited to join as a maintainer in early 2023. And earlier this year, I joined the technical steering committee, which allows me to have a broader impact on Homebrew's technical decisions and direction. So yeah, now let's dive into the first main topic of the talk, how Homebrew handles bottles and CI infrastructure at scale. So what exactly are bottles? So in short, bottles are pre-built binary packages. They are gzipped tarballs that contain the binaries, along with some metadata, and they allow users to avoid lengthy compilation time. So instead of spending minutes or even hours compiling software from source, we can install bottles in seconds. And bottles are generally platform specific because binaries are generally platform specific, and that means we build separate bottles for all the platforms that we support. And now, why do bottles matter so much? There are several key reasons, and the first is speed, because installing from a bottle takes at most a few seconds, whereas building from source you can take minutes to multiple hours for those complex software. And the second is reliability, because bottles are pre-tested builds. users know that they are getting something that's pre-tested and that works. And the third is user experience, because users don't need to compile from source themselves. They don't need to worry about having all the build dependencies installed, which can turn out to be quite huge for some complex software. And fourth, energy. And by energy, I mean both environmentally and mentally. And building from source wastes energy, especially for large packages, and that can be bad for the environment. We want to be environmental friendly, and also an unpleasant experience, especially for those on limited battery power, for example. Yeah, so how do we build and distribute bottles at scale? So let's take a look at our CI infrastructure. So we run a fully automated pipeline on GitHub Actions. So for macOS builds, we mostly use virtual machines backed by self-hosted Mac minis for both Intel and Apple Silicon architectures. And a key aspect is that the VMs are ephemeral, which means they are created and destroyed for each single build job. And this ensures clean and consistent and, more importantly, secure builds. And for Linux builds, we mainly use containers on GitHub hosted runners. And the build process is automatic. So when we have a formula update from pull requests, GitHub pull requests, build jobs are triggered automatically. And when all steps pass, the bottles are uploaded to GitHub packages where distribution happens. So a key benefit of relying on GitHub packages and on GitHub Actions in general is that we don't need to worry about manage too much infrastructure, and that is particularly important for a volunteer-driven project like Homebrew. So yeah, now let me walk you through our build pipeline step by step. So first, a contributor or a maintainer submits a pull request with a formula change. And then the CI system schedules builds on the appropriate runners based on the platforms that need bottles. And on each of the platforms, the formula goes through several steps. We fetch the formula from source, we build it, and we also audit the formula. And that includes checking things like binary linkage and directory structures and other properties to ensure that they adhere to Homebrew's quality standards. And also we run minimal tests to verify that the formula works as expected. And you can see that the steps here in this screenshot, we fetch the formula with brew fetch, and then we install the bottle, we run audits, and we generate the bottle with brew bottle, and then we also test the bottle with brew test. So a crucial step is that we also test all the dependents to ensure compatibility. So if a formula is updated, we need to make sure that all of the formula that depend on this updated formula still works correctly, and if not, we need to fix them or just update them, rebuild them as well. So this screenshot shows the dependent test workflow where we test all the dependents of a formula. There can be many of them, and this is crucial because we don't want to we don't want to break any of the packages that depend on it when we update a new formula to a new version, for example. And if everything passes and the changes are approved, we upload the bottles and commit the changes back to the formula file. And finally, after some final checks, style checks, audits, the pull request is automatically merged. So here's a real example of the bottle specifications, also known as DSL, for a formula. So the bottle block here lists the SHA-256 checksums for each platform's bottle. And you'll notice different types of seller specifications here. So sellers are essentially another Homebrew term that specifies where the bottle eventually gets installed on the user system. And the any designation means that the bottle can be installed anywhere on the file system subject to relocation mechanisms that Homebrew handles during installation. So in general, binaries installed to one location cannot be moved to another location because they may contain hard-coded paths. And relocation here means that for some binaries, it's possible for us to fix up those hard-coded paths so that they continue to work even when they move to a different location. And then the any skip relocation designation means that the bottle can be safely installed to any location we want without any post-installation fixes necessary. And this is typically for software that doesn't have any hard-coded paths. And finally, if there's no designation at all, it means that the bottle cannot be relocated at all. And if the user's Homebrew installation is not at the default location, maybe due to permission problems or maybe just for fun, and a formula will need to be built from source instead. And these destinations are determined automatically during the bottle generation process based on the contents of the bottle. Yes, and now when it comes to testing, I'll show you a real test example from the OpenJDK formula. And this test just creates a simple hello world Java program, compiles it, and then runs it to verify the output. So the key thing to notice here is that this test is very minimal. And we don't extensively test all of the software's functionalities because that's not possible anyway. And instead, we are just verifying that the basic functionality works. And this is because the aim of the test is really to catch breakage from the builds rather than to verify that the build is bug-free, which is, again, not possible anyway. And it's not a responsibility for us as downstream packagers to do so. Yeah. And the minimal tests catch, this philosophy is important because we want to catch breakage, but we don't want tests to be so extensive and slow that they slow down the entire CI system or introduce flakiness. Okay, so now I've talked about bottles and the build pipeline. Let me talk about the scale that we are operating at. So on a typical day, we process several hundreds of normal builds. And some of them are version bumps, some of them are dependency updates, and some are fixes to the formulae. And during mass bottling events, which I'll shortly explain, this can spike up to 2,000 builds in a single day. But the thing is, we have limited CI runners, so it's important for us to manage them efficiently to keep the build queue moving. So in terms of storage, again, our bottles are stored on GitHub packages as binary blobs, and they range in size from a few kilobytes to several gigabytes, depending on the formula. And in terms of usage, we see about 1 million of the installation events daily, and you can see detailed analytics at the website here, formula.brew.sh. So managing CI at this scale comes with several challenges, and the first is build time management. So basically, we don't want any single build to take too long when they shouldn't. So we impose timeouts. On macOS, normal builds have a 1-hour timeout to prevent excessive resource consumption or even starvation. And if a formula indeed needs longer time, it will be, maintainers can label the request as long build, and then the build job will be placed on a separate queue where jobs can take as much time as needed. So next, we need to minify flaky builds, which are builds that fail intermittently for non-deterministic reasons, like network issues or resource constraints. So for network issues, we retry several times in a single run before giving up so that a transient network problem doesn't cause a build job to completely fail, which then we will have to rerun the whole job, which is not good. And for minimizing flaky builds, one of the strategies to use is reproducible builds, which is also important in terms of security. And this is on its own a very complex topic, and that's beyond the scope of this talk, but if you're interested, you can check out reproduciblebuilds.org for more information. And we also, as mentioned earlier, we keep the tests minimal and robust so that we focus on basic functionality rather than the full test suite. And finally, for resource constraints, we maintain separate queues from normal builds, long builds, and mass bottling builds. And this prevents long-running builds from blocking the normal pull requests completely, which is essential for keeping development velocity high. So now I'm going to talk about mass bottling events, which are one of the most interesting scalability challenges that we face. So basically, it happens when there's a new macOS rollout or when we add support for a new platform. And this is when we bottle all of the formulae in the core repository for the new platform. And typically for macOS, we start mass bottling when the release candidate is available. And this happens usually just 1 week before the official release. And since we want to have bottles ready by the time that the new macOS release is out, we will face a very tight time constraint. So due to the time constraint, we can easily have up to 2,000 builds in a single day. And the process works like this. So we run a command called brew unbottled that lists out all the formula that need bottles for the given platform. So as you can see here, the command lists out all the formula that needs bottles from the ARM64 Tahoe system on Apple Silicon. And they are sorted by the size of dependent tree, or in other words, the number of formula that depend on them. And we want to prioritize those with the higher number of dependents so that they don't block other formulae from being bottled. And then also we use a command called brew dispatch build bottle to trigger GitHub Actions workflows run in bulk. And for successful builds, the bottles are uploaded, and the bottle specifications, the bottle DSLs, are committed via pull requests. And for failed builds, a command is posted on the tracking issue so that maintainers can triage and fix them. And to manage this, we also have a dashboard that tracks progress and highlights failures that need attention. And here's this dashboard. It's called the Mass Bottling Manager, and you can see the progress of the mass bottling event in terms of how many bottles have been successfully built and how many are pending. And this visualization gives useful information for coordinating work among maintainers during these high-intensity events. Okay, so now let me also give you a concrete example of how this scaling enables us to support new platforms quickly. So last month, before macOS Tahoe was officially released, we built over 7,200 bottles within 1 week. And during this process, we fixed over 500 build issues. These issues were mostly specific to the new macOS version, things like new compiler versions, deprecated libraries, and other macOS-specific changes. And the result was that by the time macOS Tahoe was officially released, we already had bottles ready to use for most formulae. And this was accomplished by a small team of volunteers, led by 10 people. And this really demonstrates the efficiency of our automated system, and it's a perfect example of how scaling our CI infrastructure enables us to provide a rapid platform support. Okay, so now that I've just discussed new macOS support, I'd like to shift gears and talk about our work on ARM64 Linux support, which is another big achievement, a big advancement in terms of Homebrew's platform support. So let me provide some context. So basically, Homebrew has supported Linux for years, but only on the 64-bit x86 architecture. So Linux users appreciate Homebrew for several reasons, like they can install up-to-date packages that may not be available in the distro package manager like apt. And they can do this without root privileges, and it's useful for people on shared systems like maybe the SoC computing cluster. And they get a consistent experience across macOS and Linux, which is valuable if they work on both platforms. So why did we decide to support ARM64 Linux anyway? So I identified 3 key user groups who would benefit. And the first is Apple Silicon users who run containers or virtual machines, and they want to run ARM64 Linux natively for better performance. And secondly, ARM64 Linux device owners, like maybe Raspberry Pi users, and who want to maintain a modern package manager. And I myself use Homebrew on my Raspberry Pis even before we had official support. And it was troublesome, but it worked. And the third, cloud users on ARM64 instances, maybe AWS Graviton, and where ARM64 offers a more cost-effective option, basically. And beyond those user groups, there was strong interest in the community and among maintainers in ARM64 Linux support, and I myself was an active advocate for this. And so the turning point for ARM64 Linux support came from an external factor. Before January this year, ARM64 Linux was mostly used by hobby users like myself, building packages on their own machines. and there was a lack of CI coverage that was scalable and financially viable for us. But in January this year, after a long private beta period, basically GitHub finally announced free ARM64 Linux runners for public repos. And this was a game changer that made ARM64 Linux support feasible for us. So then in February this year, at our annual general meeting in Brussels, we made the decision to officially support ARM64 Linux. And this decision allowed us to start planning to provide support for the platform. And now let me walk you through the roadmap that we followed. So in January, we released Portable Ruby for ARM64 Linux. So if you're not familiar with Portable Ruby, don't worry, I'll touch on it in a bit. And also in January, we implemented support for bootstrapping glibc, which again, I'll explain in more detail shortly after. And in February, we provided Docker images for ARM64 Linux, which enabled us to run build jobs in a consistent environment on GitHub Actions. And in March, we also prepared the CI infrastructure. We did so by setting up GitHub-hosted runners for most builds. We have not yet had a self-hosted runner for long timeout builds, but that's in the plan too. And also on the same month, we started mass bottling for the official formula, and this work is still ongoing. And in April also, we added installer support, so new users can now easily install Homebrew on ARM64 Linux with the official installation script. So now before going further, I'll explain what Portable Ruby is, since it's a crucial piece of our infrastructure. So Homebrew is written in Ruby, so having a reliable Ruby runtime is important. And Portable Ruby is Homebrew's relocatable build of Ruby that can be run, installed on anywhere on the file system. So we build it with special compiler flags against an older glibc version to ensure portability across different Linux distros. Again, I'll touch on glibc very soon. So anyway, the key point is that it's essential to providing a consistent Homebrew experience to all users, which of course include ARM64 Linux users. And finally, Portable Ruby is managed and installed automatically by Homebrew if needed, so users don't have to worry about setting up Ruby runtime themselves. And the result is basically a seamless experience for those users who don't need to, because the users don't need to manually set up the Ruby before installing Homebrew. Okay, and now supporting ARM64 Linux came also with several technical challenges, and the first is architecture-specific issues. So some software simply can't run on ARM64 at all, and we can't and won't bottle those. And some other software requires tweaks, in terms of patches or other fixes to build correctly, and we need to handle those on a case-by-case basis, really. And to fix those builds, we often need to work with upstream projects, that mean the project maintainers, to get the fix merged, which requires coordination and patience. And we also face CI capacity and maintainer bandwidth constraints. So even with free runners, we still need maintainer time to triage issues and fix build problems, and that can be a bottleneck too. And finally, we need to handle glibc bootstrapping. So I've talked a lot about glibc bootstrapping, a lot about glibc, but what's the matter with it? So for context, glibc is NUS C library, which is the standard C library used by most Linux distros. Note that Homebrew currently only supports GNU Linux with glibc, so not other libc implementation like Muscle, which you can find in, for example, Alpine Linux. And glibc offers backward compatibility, which means that binaries built against an older version of glibc can run on systems with newer versions, but not the other way around. So that's where the challenge is coming in. So here's the problem. We built our software on Ubuntu 22.04 with glibc version 235. However, some users are on older distros with older glibc versions. So for example, if you're on Debian 11, then you're running glibc 231. And as I mentioned earlier, glibc lacks forward compatibility, which means that our binaries will not work against these older versions of glibc. So our solution, which had already been implemented for 64-bit x86 Linux, is to provide a homebrew managed glibc that gets automatically installed when the system glibc is too old. And then we depend all the bottled formulae on this version of glibc. And the bootstrapping requirement is that we must be able to build this glibc without homebrew dependencies, because otherwise we would have created a circular dependency. And to achieve this, we built a minimum collection of tools, including GCC, bin utils like the linker, and and other essential tools against the oldest system glibc version that we want to support, so that it can be used on older systems to build glibc itself. So for ARM64 Linux specifically, this is glibc 2.17, which is significant because this happens to be the first version of glibc that supports the architecture. But why does this matter? It's because building against an older glibc ensures maximum compatibility and portability so that we can support a wider range of Linux distros, which is another key aspect of scalability. Okay, so now let's move on and look at where we are today with ARM64 Linux support. So we have bottle coverage for approximately 5,700 formulae, which represents about 90% of the formulae in Homebrew core that are compatible with ARM64 Linux. And ARM64 Linux is currently at Tier 2 support level, which means it's subpar but usable. More on that later. And in terms of adoption, analytics suggest that ARM64 Linux accounts for about 0.6% of all Homebrew analytics events in the past 30 days. And that number might sound small, but it's because the majority of Homebrew users are on macOS. And in fact, if you only consider Linux, ARM64 Linux accounts for roughly 1 in 20 installation events or other analytics events, which is a good start. And we expect adoption to continue to grow because Apple Silicon becomes more prevalent and ARM processors in general become more widely adopted. And we also improve bottle coverage and the overall support level so that more users can benefit from Homebrew on ARM64 Linux. And all these analytics data is publicly available. So if you're interested, you can check it out again at formula.brew.sh. And now, since I've mentioned about support tiers, let me explain a bit about them. So basically, Homebrew support tier models helps to set expectation for users. So tier 1 is the best support level with the best experience, full CI coverage, and active bug fixes. And this includes macOS versions that Apple supports. And for those of you who don't know, Apple supports the latest 3 major macOS releases for both Intel and Apple Silicon. And we also support 64-bit x86 Linux with newer glibc versions. And tier 2, where ARM64 Linux is currently at, means subpar but usable experience. We have partial CI coverage, and we review pull requests, but we don't actively fix all bugs ourselves. And other tier 2 platforms include macOS pre-releases. This happens, generally after WWDC, and also 64-bit x86 Linux systems with older glibc versions. And finally, tier 3 is for configs with a poor experience, no CI coverage at all, and a very high bar for accepting pull requests that fix issues. And this includes very old macOS versions and non-standard installation prefixes. And finally, if a platform is not in one of those tiers, it's considered unsupported, meaning no support at all. And examples include like FreeBSD. We've been asked about this many times. No. And ancient macOS versions when it was still called, macOS 10. And, Minecraft Redstone computers for obvious reasons. And iOS. And it doesn't help if you jailbreak it either, which I happened to be asked yesterday on GitHub's discussion forum. Yeah, so no iOS support, don't expect it. Yes, and to read more about the support tiers, you can check out the documentation at the URL shown here. So now looking forward, what are our plans for ARM64 Linux? So we'll continue to improve bottle coverage with a goal of eventually reaching full coverage for compatible formulae. And we are working on the completing the self-hosted runner setup for long builds. It takes some time because of some architectural changes, but it's in progress. And once we reach significant coverage and become confident in the stability, then we may increase the support level to ARM64 Linux to Tier 1 support. And that actually depends on sustained maintainer bandwidth and also resource availability. And also, of course, we are an open source project. So throughout this process, we also encourage community contributions like porting formulae, reporting issues, and even better, submitting patches. All are very welcome. Okay, so now let me wrap up by tying everything back to the talk's topic, homebrew at scale. What are the key lessons that we've learned? So first, leverage platform resources over self-hosted runners when possible. So by using GitHub packages for distribution and GitHub hosted runners for certain builds, we care less about managing infrastructure. And this reduces both cost and maintenance burdens, which is crucial for a volunteer-driven project. And second, fully automated workflows are essential. So our entire CI pipeline from PR submission to formula build to bottling and merge all happens automatically. And when mass bottling is concerned, tools like brew unbottled, brew dispatch build bottle, and the mass bottling manager dashboard, they essentially allow us to handle over 2,000 builds per day with minimal human intervention. And third is minimal and robust testing philosophy. It reduces build times and flakiness at scale. So by focusing on basic functionality rather than full test suites, we can test thousands of formulas efficiently. And then scalability, which enables new architectures. And the availability of GitHub-provided ARM64 Linux runners enabled us to support a newer platform without incurring significant cost of maintenance overhead. And we can then scale to new user bases efficiently. And finally, a phased approach is essential for sustainable scaling because we first plan ahead for ARM64 Linux support, and then we prioritize building infrastructure, and then started mass bottling. And this approach allowed us to make steady progress with confidence and avoid taking wrong turns and wasting our efforts. And this is particularly important, again, for resource-constrained projects. So with that, thank you for your attention. If you have any questions or want to get in touch, so these are the ways to reach me. And you can reach me via email. Check out my LinkedIn profile. It's on my website. And you can also follow me on GitHub. Yeah, thank you. Yeah. Any questions? Yes.
Just out of curiosity, does Homebrew have incremental building or maybe caching the steps between for deploy or building?
Yes, we do have a thing called bottle cache, but when it comes to caching, I'm not sure if you have heard about the saying that caching is one of the hardest computer science problems. So basically, yes, we do have bottle caching, and it's used when we force push to a branch and the formula happens to be untouched because in a pull request there can be many formula changes, and if we confirm that a formula is unchanged, then the bottle cache will be used, and we won't be building the bottle again, and we reuse the bottle from the previous workflow run. Yeah.
Oh, but usually it's quite manual to decide whether
it's automatic.
Oh.
Yes. Yes.
So you mentioned that your ARM64 Mac runners are all self-hosted, right? So where do you host these runners and how do you manage them?
On Mac Stadium. So I'll touch a little bit more on why we manage this self-hosted instead of relying on GitHub-hosted runners. It's because the GitHub-hosted runners come with an abundance of build tools that we don't want to use, and because they can interfere with our build process, which is not good. And also we rely on we do rely on self-hosted because on Mac Stadium, because they reach out to us, and they happen to be able to manage the infrastructure for us, and so it's good to rely on something that rely on somebody that handles all the dirty work for us, basically.
The capability to automatically deploy all those VMs and stuff that when you start your CI builds.
Yes, we do have a CI orchestrator for that purpose. Yes.
Are you planning to add support for multi-user on macOS without compiling on resource?
Yes. If you actually look at our documentation website, I think it's possible. So basically, you need to set up a new dedicated user for the Homebrew installation, and for other users, they sudo to that specific Homebrew user and do the installation.
I see.
Thank
But
you.
is it possible to isolate the packages within a user?
There's currently not supported, so yeah, you have to either install it to your home directory, which falls under the tier 3 support. Yeah. Okay. Any other questions?
Regarding your Linux ARM64 builds, on macOS, for M1 Macs, like there's a version of Linux ported to it. There's a debate within 16K and 4K page sizes. Do you all support both versions, or do you only support macOS 16K page sizes?
You mean page sizes?
Yeah. Like programs compiled for 4K. Programs compiled for the 4K page size will not work effectively on the 16K.
Yes, and there's actually a very similar problem for, as far as I know, for Raspberry Pi OS as well, because
As long as it's ARM-based, it will be effective. So do you all
yes.
provide both 16 and 4, or do you all provide only 16
We provide support for the so for the most basic configuration, which I believe is 4K page size. But there was some recent changes that I wasn't involved that involved, adding support for 16K page sizes. Thank you. Yes, and any other questions? Okay, if not, thank you again. Yeah.